Hi everyone, so for today we'll be working on a solution for problem set 4, which is filter less comfortable. So in this problem set, we'll be learning how to apply filters to images. So for file formats like BMP, JPEG and PNG, they support 24-bit color using 24 bits per pixel. So these 24 bits consist of 8 bits that signal the amount of red, 8 bits that signal the amount of green, and another 8 bits that signal the amount of blue. So together, this gives you the 24 bits that determine the color of that particular pixel, and the respective values of R, G and B is between 0 and 255. So in an image file, the bits are actually arranged in a sequence where every group of 24 bits tells you the color of each pixel, which in turn will give you the image. Besides these bits, files also contain metadata, which contains information like the image height and width. So before we dive in, do remember to like this video and also subscribe to my channel. I really appreciate it when viewers subscribe or leave comments about how you find the videos helpful. It really makes my day, and thank you so much for your support. Now moving on, let's talk about image filters and how they work. So essentially, an image filter involves a code that will change the pixel's color by a certain shade to achieve the desired outcome. So let's first talk about Grayscale, where you change a color image into varying shades of grey. So when the RGB value is 000, you get black, and when RGB is 255 for RG and B, you get white. So when your values of RGB are all equal, you will actually get varying shades of grey. So the closer you are to RGB each being 255, the lighter the shade of grey, and the closer you are to RGB being each 0, the darker the shade of grey. For every pixel that you are converting to grey, you actually just need to take the average of the RGB values to determine the shade of grey of the new pixel. So in this example, where R equals to 14, G equals to 120, and B equals to 190, you just need to actually add all of these up and divide by 3, which will give you 108. So the resulting color of the pixel would be RGB being each 108. So moving on to the next filter, Sepia, it gives images an old-timey feel. So this is done by applying an algorithm to each pixel. So since the resulting value may not be an integer, this means that after we apply the algorithm, we need to round the value to the nearest integer. And if a new value is more than 255, then you need to cap the value at 255. Moving on to the next filter for reflect, this is done by flipping the image horizontally, and it's actually done by moving pixels around. So pixels on the left of the image will end up on the right, and vice versa, and there is no change to the value of the pixels, only their horizontal position is changed. So in this example, the pixel will actually be moved to the end of the row, and the next pixel will be moved accordingly, and so on and so forth for the rest of the pixels. Next, for blur, this actually creates the effect of blurring and softening the image. This is done by changing the value of the pixel to the average value of its neighbouring pixels. So let's look at this image for example, and let's say we are working on the highlighted pixel 6. So to find the new value of this pixel when we want to blur it, we need to take the average of the surrounding pixels. So in this case, the new value of the 6th pixel is the average of 1, 2, 3, 5, 6, 7, 9, 10 and 11 divide by 9. Now, what happens if the pixel is on the edge? Its new value will be the average of the sum of 10, 11, 12, 14, 15, 16 divide by 6. So there are actually 4 functions that we need to write, which are Grayscale, Sepia, Reflect and Blur. But first, let's load the distribution code to see the files and code given. There are actually quite a number of files and it might seem overwhelming, but actually we just need to work only on one file. So let's just go through what each of the files does. First, we have images, which contains sample images for us to work with. Then we have bmp.h, which stores information about bitmap images and stores the struct needed to complete the assignment. Next, filter.c is the program that we will run these filters. And later on, when we make a filter, the image with the filter applied will be saved as a brand new file. Helpers.c contains the functions that we are going to implement, so we'll be working out of the helpers.c file. Helpers.h is the header file that declares all functions that show up in helpers.c. And lastly, makefile actually combines all the above files into an executable file. So even though we're writing the functions in helpers.c, to compile the program later, we will still do makefilter. So actually, we just need to look at 2 files in detail. So first is bmp.h. You can see that for this portion, it defines the struct. RGB triple represents a pixel with red, green and blue values. So for example, in this image below, you can see that actually an image is a 2D array, which I think we have come to be quite familiar with. So for the first pixel, its position is where I equals to 0 and J equals to 0. So the values of RGB can each be represented as such. Likewise, for the next pixel here, its position is image 3, 1, and the RGB values are each 255. Next, for helpers.c, it shows the sections for us to write each function. So for this section, there is Grayscale and Sepia for us to input. And for the next part, it will be reflect and blur. So these are the 4 functions for us to code. Now, Grayscale and Sepia is actually more straightforward, so I'll go through this a bit quicker, as we'll be spending more time on reflect and blur. So let's start with Grayscale. So as discussed earlier, we need the average RGB value of the pixel to determine the shade of grey. So this is the part of the distribution code for us to work with. So let's look at this image for example. The values of RGB are integers and we actually need to find the average value. So the resulting RGB value may actually not be an integer, such as this example below. So let's say your RGB is 104, 127 and 173. The resulting average is actually 134.67. So this means that we should convert the integer values of RGB to float first, find the average value, then round the value to the nearest integer. So the overall structure would be, we will first look through I and j to ensure that we look through every pixel in the image. Then we will convert each of these RGB values to float. We will find the average and we will update each of these values to the new average value that we have found. So let's put this in C. So we'll start by putting in a comment that we will start combing through each row first. So we'll do our for loop through the row, which is represented by I. And next, we will also comb through each column. So I'll just put in a comment here. And we will comb through J, which represents the column. Next, we want to convert the pixels to float, as we discussed earlier on. So let me put a comment here. Okay, so we will have float rate equals to image ij RGBT rate. And we will do the same for green and blue. Next, we will just find the average and update the pixel value accordingly. So again, we'll just put a comment here. And the average, remember, we need to actually round the sum of red, green and blue divided by 3 to convert it into an integer. And then now what we'll say is that the RGBT red, green and blue value will all equals to the average. Right, and actually that's all you need to do for Grayscale. So now let's make filter. Now let's apply it to one of the images that we have in our folder. Okay, so now we'll open out file. And there you go, you can see that it's grey, and that will be the solution for Grayscale. So now let's move on to Sepia. So as discussed, we will apply the algorithm to the new RGB values. But if the resulting R, G or B value is more than 255, we will cap the value at 255. So to recap, this is the algorithm, where we will need to get the new values of red, green and blue based on these equations, and we will use sepia red, sepia green and sepia blue to represent these. So we will first convert the original RGB values to float first. So the overall structure of our code will look like this. We will first look through I and j to ensure that we go through every pixel in the image. Then we will convert each of the RGB values to float. We will apply the algorithm to get our new RGB values. But if it's greater than 255, we will fix the value at 255. Then we will update the value of the pixels accordingly. Okay, and let's put this in C. For Sepia, what we'll do again, we will comb through each row. Then again, we will comb through each column. And before we apply the algorithm, we will convert the pixels to float first. Right, so there will be float original rate, equals to image ij.rgbt_rate, and again we will do that for green and blue. Now we will apply the algorithm to find the updated pixel value. So we'll say that we have an integer called sepia rate, and remember we must actually round the result that we will get by applying this equation to the color that we need. So what happens, right, is that we are already given the formula for the respective values for sepia red, sepia green, and sepia blue. So we just need to apply it while remembering to include the round function inside. So I'll just quickly paste it in for green and blue. Okay. Now what happens if the value of sepia red, green, or blue is above 255? So we actually need to update that if it exceeds 255, we will just put the value as 255. So if sepia red is greater than 255, sepia red will just simply equals to 255. And we'll repeat this step for sepia green and sepia blue. And now that we have our final values for sepia red, green, and blue, what we need to do is just to update the final pixel values, where now the color of RGB of every pixel within the image will just equals to sepia red, sepia green, and sepia blue. Okay, so remember to hit Ctrl S to save this program before you make filter. So let's try it out. Where it compiled. So now let's apply this to one of the images in the folder that we have. I'll name it as outfile2. Now when I open it, we'll hope to see a sepia image, and there you go. So this is how sepia filter works. Next, we will work on reflect. So this is done by only changing the horizontal positions of the pixels. So in this example, you can see that we flip the position of each pixel. One moves to the end, but notice for pixel 3, it is in the middle of the image and it remains in the position as it is in the reflected image. So how do we do this? We are actually trying to reverse the array, and we will do so through the use of temp. So first we will need to remove 1 from its original position, but where does this go? So we will store it in a temporary variable called temp. And now that the cell is empty, we can shift the value of the last pixel into this position. So the pixel value is now updated. And then we will assign the temp value into the end of the array. So now we need to find out how to define the position of the pixel that we are swapping with. So what does this look like in code? So let's use an example where we need to reverse this array. So as we look through this 2D array, you can see that when j equals to 0, the value is 94, and we will swap this with 12 where j equals to 4. I will leave remarks blank for now. Then moving on, when j equals to 1, the value is 46, and we will swap this with 84 where j equals to 3. Likewise, remarks is blank for now. Next, when j equals to 2 and the value is 23, notice that we do not swap it, and we keep the value as is. Then as the program continues where j equals to 3 and the value is 46, you can see that if we swap, we actually end up swapping with 84, which would mean that you are back to your original array. So notice that if your program continues to run after it crosses the halfway mark of our array, it will end up switching the numbers back to its original positions. So this means that your program should only run up to the halfway mark of this array. So this means we need to modify our loop such that the program only loops through j less than with divide by 2. So it will stop at the halfway mark. Now we need to come up with a formula to tell the program where to swap the numbers to. So for the first row where we swap 94 and 12, you can see that when j equals to 0, we are swapping the values with the pixel at j equals to 4. And moving on, when j equals to 1, we are swapping it with the value where j equals to 3. So we can actually see a pattern. For the first row, you get j equals to 4 by taking the width of the image, which is 5, minus j, which is 0, plus 1. For the second row, you can actually find the value of the j that you want to swap your value into by taking width, which is 5, minus j, which is 1, plus 1 equals to 3, which is the value of j that you're trying to swap this into. So the formula to tell the program where to swap the numbers into can be found as with minus j plus 1. So putting it together, we will actually loop through the image, create a temporary image for us to move the pixels out first. So that is RGB triple temp equals to image ij. Then we will move the new value of the pixel in, which would be image I, j equals to image I with minus j plus 1, which we have just explained. And then we will insert the value of temp into the last position. Okay, so let's put this in C. So for reflect, we will again comb through each row. And again, we'll comb through each column. And then after that, we will declare our temp. So that's RGB triple temp equals to image ij. Right, and then now we will park the new value into ij. So that will be image ij equals to image I with minus j plus 1, which is what we have discussed earlier as to how we derive this. And lastly, we will just move the value from temp into the value that we are replacing it with. And yep, so that's actually all for reflect. So what we're going to do is that again, let's make a filter and let's try it out with one of the images that we have in the folder. Right, so make filter, then we'll just apply it. And I'll rename it as outfile3.bmp. And opening up the file, you see that yes, the file has been reflected. So this is how the filter for reflect works. Next, let's work on blur. So blur is actually a little bit trickier, so I'll be spending more time on this. So for blur, this is actually done by assigning each pixel a new value which equals to the average of its neighboring pixels. So let's look at this example where we have a blue and red image. So looking at this particular pixel as an example, we will need the average of its surrounding values. So the respective R, G and B values will be based on summing up all the RGB values of the 9 pixels and getting the average. So likewise, for another pixel, we will take the RGB values accordingly. Now, what happens if the pixel is on the edge? So the program will actually still look for the 8 surrounding pixels, but it should know to ignore the pixels outside of the image. So this means that the average value will just be based on the 4 highlighted pixels here. So after we work out the average value and get our new pixel value, what do we do with it? We cannot put the pixel back into this original image because when our program moves on to the next pixel, it will actually end up factoring this new pixel as it calculates its average pixel value. So essentially, if you put your new pixel back into the original image, you will ruin the blur function as it goes through the rest of the image. So what we should do is that we should actually create a temp copy of the image, park our new pixel values there, and insert these back into the original image after we complete blurring all the pixels. So what is the overall structure of the code? So we will first create a temporary copy of our image to store our newfound average pixel values as we loop through the original image. Then we will work on blurring our image. So we will first loop through each pixel. Then we need to find its neighboring pixels, check that it's valid, and after that we need to do 2 things. Number 1, which is to calculate the sum of the respective RGB values and count the number of the valid neighboring pixels. Then we get the average value, round it off to the nearest integer, and then we will copy the new pixels into the image. So let's go step by step for this. So first, we will create a temporary copy of the image. So this is actually done by looping through each pixel of the original image and writing them into temp ij equals to image ij. So by doing so, you are just directly copying each pixel over. So next, we actually need to loop through each pixel to find its neighboring pixels. So let's take a closer look at this particular one that we're looking at, which is the first pixel of this entire image. Right. So to find this particular pixel, we will use our usual loop to go through this 2D array. So we will loop through I for the rows and J for the columns. So for every pixel that we loop through, we need to take a closer look at its neighboring pixels. So for now, we will ignore as to whether the pixel is valid or not. We will first focus on getting the neighboring pixels. So let's zoom in on this particular grid of 9 pixels. So this is the close-up of the grid that we are looking at. And what this grid shows is that it shows the coordinates of the neighboring pixels that are relative to the pixel that we are looking at. Okay, so because now we are looking at the coordinates of the neighboring pixels relative to the pixel, let's use x and y to represent it so we do not confuse it with I and j. So for the horizontal position of the neighboring pixels, it's represented by x, and it ranges from -1 to 1. And for the vertical position represented by y, it ranges from -1 to 1 as well. So hence, to find the neighboring pixels, we actually need to use another loop. So in a way, we're actually doing a loop within an overall bigger loop. So for int x equals to -1, and as long as x is less than 2, since the max value of x is 1 that we have just discussed, x will increase incrementally. And then now we will look through the columns where int y equals to -1, and y is also less than 2, since the max value of y is also 1, and this will increase incrementally by 1. So by doing this, what this loop does is actually to identify the neighboring pixels. Next, we need to determine the scenarios in which the pixels are invalid, and this will actually be when the pixels are along the edge of an image. So to do so, we first need the exact coordinates of these neighboring pixels. So in this example where we're looking at a pixel where I equals to 0 and j equals to 0, you can see that the coordinates of the highlighted pixel here is -1 and -1. So in another example where we're looking at a pixel where I equals to 2 and j equals to 3, the relative position of the circled pixel occurs when x equals to -1 and y equals to -1 from the original pixel. So the coordinates for this neighboring pixel can actually be defined as current x equals to 2, which is the I position of the current pixel that we're looking at, plus -1, which is the relative position of this pixel, equals to 1. And likewise for the y value, current y equals to 3, which is the j position of the current pixel, plus -1, which is the relative position of the pixel, right? So with that, we can actually shortlist the formula to find the coordinates of each neighboring pixel, and it's actually represented by int current x equals to I plus x, int current y equals to j plus y. So now we'll use another example just to check whether this formula is correct. So let's look at another pixel where I equals to 2 and j equals to 3. So for the highlighted pixel that we're looking at, int current x equals to I plus x equals to 2, which is the I position of the current pixel, plus x, which is 0, equals to 2. And moving on, int current y equals to j plus y, and in this case, it equals to 3, which is the current j value of the pixel that we're looking at, plus 1, equals to 4, which will give us the coordinates 2, 4, which is correct as per the image we see here. Okay, so now what we have done is that we have come up with a formula to identify the exact coordinates of each neighboring pixel. Okay, so now that we have that, we need to skip the invalid ones. So where are the invalid pixels in the image below? It happens when the pixels are outside of the image. So in this example below, height equals to 4 and the width equals to 6. So let's start by writing down the coordinates of the invalid pixels to find a formula for us to apply, such that when the conditions are met, the pixels are deemed invalid. Starting with the top row, notice that the pixels are invalid as long as x, which is the position of the pixel along the row, is less than 0. Next, let's look at the leftmost column. Notice that the pixels are invalid as long as y, which is the vertical position of the pixel, is less than 0. We move on to the bottom row, where you can see that the pixels are invalid when x equals to or is greater than 4, which is the height, which we can express it as current x is greater than height minus 1. So as long as current x is greater than 3, the pixels are invalid. And lastly, for the rightmost column, the pixels are invalid when y equals to or is greater than 6, which we can express as current y greater than width minus 1. So far what we've done is to find the valid neighboring pixels. Next, we need to find the average value of valid neighboring pixels. So to do so, we actually need to find the total sum of the rate values, which we can express as plus equals image current x current y RGB rate, which essentially means that you are adding up all the valid neighboring pixels to total rate. Then we do the same for total green and total blue. So as we do this, we need to count the total number of valid neighboring pixels. So we actually will express this as counter plus plus. Then we will calculate the average and insert these new pixels into our image. And let's put this in C. For reflect, we will first create a copy of the image. So we'll do so by doing RGB triple, temp height, and width. Okay, so what we'll do is that we'll look through again the rows and the columns of the image. And we'll just say temp ij equals to image ij. So what we are doing now is just to directly copy over the pixels from the original image into this temporary one that you are making. Okay? Now moving on, we will do by looping through the image, and we'll go through every pixel. So we will just look through the rows again, and now we'll look through the columns. And at this stage, what we're going to do is that we're going to declare that there will be an integer called total red, total blue, and total green. So what this actually represents would be the total number of valid neighboring pixels that we will be working with. Right, and the counter starts with 0. So we'll be using this later. So now let's get the neighboring pixels, which is what we've been working on. So remember, we'll do for int x equals to -1 and x less than 2. That is the range of the relative positions of our neighboring pixels. Likewise for y, which represents the vertical positions of the relative neighboring pixels. And as we have worked out just now, the current x value, which is int current x, equals to I plus x. And again, int current y equals to j plus y. Now we need to check if the neighboring pixel is valid. So remember, we went through the 4 conditions just now. So if current x is less than 0, or if current x is greater than height -1, or if current y is less than 0, and lastly, or if current y is greater than width -1. Okay, so what happens is that we'll put continue. So what continue essentially does is that if it is an invalid pixel, the loop will just continue to run. So if it's invalid, we will skip and continue looping through. Okay, then now we will get the image value. So total red will basically means that you will add up all the valid neighboring pixels that you have. So you will add up all the red values here. And we'll do the same for total green, where we'll add up all the values for green of the valid neighboring pixels. And again, for total blue, we will do the same for the valid neighboring pixels, where we add up all the blue values. And as we are adding up, do remember we also need to count the number of valid neighboring pixels that we are working with, and that is where counter will come in, where we will add to the counter incrementally every time we come across a valid neighboring pixel. Okay? Then now what we need to do is that we need to calculate the average of the neighboring pixels. So now we're going to say that the new pixel value, which is represented as temp ij, RGBT red for the red value, equals, where we need to round it up, so we will round total red divide by counter, and again we repeat the similar steps for green and blue. So now we have the value of the new RGB that we need. So now what we need to do is just to copy these values into the original image. So we're going to look through the original image. So again, looping across the rows and looping across the columns. Right, and now we will see that we're basically updating every pixel, where image ij RGBT red means that that particular red value for that particular pixel equals to what we have just calculated for that particular pixel after it's been blurred. So we'll do it for red, we'll do it for green, and we'll do it for blue. Okay, and yep, do remember to save, and then after that we will make filter. Then we'll apply it to one of the images that we currently have in the folder. So in this case, it will be blurring the yard.bmp image, and we'll name it as out file 4. Okay, so after we've run it, let's now open it. You can see that the image has been blurred. And there you go. So this will be the solution for problem set 4, filter less. Now, if you found this video to be helpful, I'd greatly appreciate it if you could subscribe to this channel and also like the video. This definitely helps with the algorithm and it will be recommended to others who are looking for this solution as well. Thank you so much for your time, and I'll see you in the next video.